All right, so today we're going to be finishing up chapter 29. So this is the last new material that we're going to learn before the final. So our final is a week from today. It's next Wednesday. So you'll have a full week. Our last new material we'll learn today, so you have a full week until the final at least to try to absorb and study chapter 29. So now let's get started with chapter 20, or let's finish with chapter 29. So I want to just go back to the EMF for a second. So we saw the EMF yesterday and how a changing magnetic field, or changing magnetic flux rather, can induce an EMF in some circuit. So we can rewrite what we saw in our earlier chapters, that for an ideal battery, the potential difference supplied by the battery is just equal to the EMF of that battery. So since we know now from yesterday that we can write the EMF in our circuit as the line integral of the electric field over that circuit, or over that path, that's also going to be equal to the potential difference supplied by our battery. So we can just equate all three of these quantities. So it's important to note that this is true for an ideal battery. So that means that a battery that has no internal resistance, so it has to be an ideal source. So we have no internal resistance for this to be true. And I also want to point out that even though the EMF is called the electromotive force, it's not really a force at all. So some books don't even refer to the EMF as electromotive force. They refer to it as like electromotance or something like that. So they don't refer to it as a force at all, which is probably a good idea since it's not a force. So once again, we have a name that's sort of like not ideal, since a lot of these conventions and names were developed before we really understood what was going on with electricity and magnetism. So we have this unfortunate name for something that's not really a force. So we can see from this equation, we remember that our V is the potential energy, or the work per unit charge. So this is measured in volts. So we have here the potential energy, or the work per unit charge, which is measured in volts. So we know also that the EMF is measured in volts as well. So we can see right away just from the units, we know that the electromotive force is not a force because it's not measured in newtons, it's measured in volts, which means it's a work or an energy per unit charge. So the EMF is just the work done per unit charge by the source, by that ideal battery. So again, it's not a force at all, it's a work per unit charge done by that whatever source you have. So now we're gonna apply this to what's called motional EMF. So most of the time we've seen a potential difference supplied by, or an EMF supplied by a battery, but it can also be supplied by a generator, and that's the most common basically source of EMF, is this motional EMF that's supplied by a generator, which is essentially just a moving wire in some magnetic field. So we saw this yesterday. We had the problem where we had this circuit, these two wires that are connected by this sliding wire in between them, and we move this wire to create a EMF in that, that circuit here. So motional EMF just means an EMF that's created by moving a wire through a magnetic field. So let's just look at some of the equations for this a little bit more carefully. So let's just look at the just this bar here. So forget the rest of the circuit, and we're just going to look at this bar in a uniform magnetic field, and then we're going to move it to the right with some velocity v. So our magnetic field is going into the page, our bar has some length L, and we're moving it to the right with velocity v. Now we're going to assume that we're looking at positive charges in this wire, since that's how we talk about current, is with positive charges. So as this rod is moved to the right, each of the charges in the rod is going to feel a force from the magnetic field, right? So we have the force is given by QV cross B. Now here, since our B is into the page and our velocity is to the right, that means that they're at a right angle, so our sign is just 90 degrees. So we can just write the force as QVB. And the force is going to be upward. So again, we can do that with our right hand, where we put our hand to the right in the direction of the velocity. You curl your fingers down in the direction of the magnetic field, and then you see that your thumb is pointing upward in the direction of the force. So our force is upward. So if all of these positive particles in our rod start feeling an upward force, they're going to move up, right? So all of our positive particles are going to start accumulating up here. And that means that we'll have sort of like an induced negative charge on the bottom and a positive charge on the top. And now this will set up an electric field. So now this sort of looks like a capacitor almost, where you have positive charge up here and then some empty space and then negative charges down here. So this is going to set up a corresponding or an opposing electric field in the opposite direction, right? So if we have a bunch of positive charges up here and some negative charges down here, the electric field will be pointing downward. So now our charges also feel that electric force downward. And this will happen until these two forces balance each other out. So eventually we're going to have the case where the magnetic force and the electric force here have balanced out. And we can see that our charge actually cancels, and we're left with just E is equal to V over B, V times B. And we also know what the potential difference between this top portion and this bottom portion are, since it's sort of it's just like a capacitor where we have some constant electric field going downward. So the potential between those two ends is just going to be E, the electric field between them, times the length or the distance of this rod, the distance between our two endpoints. So the potential now between here and here is the electric field times L. So I can just rewrite this. I can plug in VB for L, so I can just have VBL as the potential difference between up here and down here. Since our problem deals with the magnetic field, right, we were given a uniform magnetic field, we want to keep things in terms of the magnetic field and the velocity that we were initially given. So this now is just equal to the EMF. So this is exactly what we found yesterday when we figured out what the induced EMF was in this circuit when we moved this rod and put it, on a complete circuit. We found that the EMF was given by VBL. So whether you look at it as a change in flux or you sort of approach it this way, you'll get the same answer for the induced EMF, obviously, which is what we want, because we shouldn't expect two different answers for the same physical problem. So this is what's called motional EMF. It's an EMF that's generated by moving a wire in a magnetic field, a uniform magnetic field. So let's do an example with this motional EMF. So we have the exact same setup here, so this figure here. So we have here the rod in this figure is 0.1 meters long. So our length is 0.1 meters. The velocity is 2.5 meters per second. And then the resistance in the loop, so this loop will have some total resistance that is 0.03 ohms. And then the magnetic field is 0.6 Tesla. We want to find the motional EMF, the induced current, and the force acting on the rod. So, all right, let's first find the motional EMF, since that was the equation we just had. So for the motional EMF, that will just be VBL, which we just found. So all we have to do here is just multiply out. We have the velocity, we have the magnetic field, and we have the length. So we have 2.5 times the magnetic field is 0.6 times the length is 0.1. And again, if we approach this from the direction we did yesterday, where we looked at it as a changing flux, we would obviously get the exact same answer for the EMF. So it's a good idea also if you want to just practice sort of deriving it that way and make sure that you do get the same answer. Okay, so now we can just multiply out these numbers. So for this, we get 0.15 volts. So our induced EMF is 0.15 volts. Okay, and then we want to find the induced current. So the induced current, we just use our little our Ohm's law for EMF. So we have the EMF is equal to the current times the resistance. So to find the current, we just divide the EMF by the resistance, and we have 0.15 volts divided by 0.03 ohms resistance, and that comes out to 5 amps. So we have a 5 amp current going through this wire. And now we want to find the force acting on the rod. So to find the force, let's write that over here. So we want to find the force acting on the rod. And I should note, this is the magnetic force we want to find. So we want to find, as we move this rod here to the right through the magnetic field, what is the magnetic force that that rod will feel? So the force, we can just use our force on a current carrying wire equation. So our force will just be the current, which we found was 5 amps. Then we have to think about our cross product here. So the length, so the current we said was going up, right? The current is going in this counterclockwise direction. So on this piece of rod, the current is in the upward direction. So let's just call that, we'll say this is X and this is Y. So let's look at this cross product here. So our length is in the upward Y hat direction, and the length is just that 0.1 meters. So we'll keep that as L for now. So we have L in the Y hat direction crossed into B, which is into the page, which would be in the negative Z hat direction according to the coordinate system I set up here. So that would be negative Z hat. So Y hat crossed into negative Z hat gives me negative X hat, which is to the left in this case. So let's plug this back in. So our L was 0.1 meters, and our magnetic field was 0.6. And so this is in the negative X direction, or to the left. And you could also do this using the right hand rule. If you wanted to put your hand in the direction of the current, which is upward, and then curl your hand into the direction of the magnetic field, which is into the page downward, you'd see that now your thumb is pointing to the left. So either way you look at it, whether you do the full cross product or just use the right hand rule, you'd get the same answer, that it's going in the leftward direction, that force. So, okay, so now we just multiply out our 5 times our 0.1 times our 0.6, and we get 0.3 newtons to the left. All right, so when we pull this rod to the right with some velocity, the magnetic field will exert a force on that, and that force will be in the opposing direction, so that will be to the left with a force of 0.3 newtons. Now, let's also find the power dissipated through this circuit. So since we know that this circuit has a total resistance of 0.3 or 0.03 ohms, we can find the total power dissipated through this. So if we wanted to find the power dissipated, we could use this equation. I'll call that P dissipated. We could just use this equation that we saw in one of our previous chapters. And we know what the current is, right? So I don't want to plug in any numbers yet, so let's just use, we found the current was E over R. So our current here, was E over R. And we said that the EMF was VBL. So I'm just going to replace that. And then if we just multiply this out, we get V squared, B squared, L squared over R, because this R and the R in the bottom, the R squared in the bottom cancel. So this is how much power is dissipated in this circuit here. So if power is being dissipated in the circuit, and we said that the magnetic force does no work, you can ask, like, well, what's doing the work? Something, power is being dissipated, there's a current flowing, something has to be doing work, and that thing is us. So whoever's moving the wire to the right, that's what's supplying the energy, that's what's supplying, doing the work to make this EMF move. It's not the magnetic field. Like we said, the magnetic field can never do work. So it is you or me, whoever is moving that wire, that's who's doing the work. And whoever is applying work to this system is doing it at the exact same rate that the power is being dissipated. So this is both the power that's dissipated in this circuit and the power that's applied to the circuit or supplied. So now let's talk a little bit more about Faraday's law. So there are really three different things that are going on with Faraday's law that are all kind of just lumped together under one name. So Faraday did these different experiments. He did three different setups, and he did this in 1831. And now this is important because Maxwell's equations weren't developed until like 1862 and in the later 1860s. So, we really didn't understand how electricity and magnetism worked at this point. So there were three different things that he did. The first thing he did was what we just saw, which was the motional EMF setup. So he had some magnetic field here. So we have some constant magnetic field going into the page here. And he took a loop of wire that had some resistance to it. And he just took that wire and basically like moved it over the magnetic field and then moved it out of the magnetic field and just did that. And he would see that as he moved it and as it entered the magnetic field, a current would flow. So that's one thing he did. He moved a wire into and out of a magnetic field. Then he did a second experiment. He moved the magnet itself. So he kept the wire still. So he held the wire still on some apparatus and then moved the magnet underneath it. And he saw that the exact same current would flow. The exact same type of current would flow in that wire, just as when he had moved the wire itself and left the magnet still. So then the third thing he did was he kept both the magnet still and the wire loop still. And then he just changed the strength of the magnetic field. And again, he saw that a current would flow. So these three experiments are really what are sort of the basis for relativity, because we might not think it's that interesting, but relativity hadn't been developed yet. So still having this ultimate frame of reference was still very much in physicists' minds. So to us, it might be like, okay, well, yeah, just the relative motion of the magnet and the wire is what matters. But to them, they didn't have that notion yet of like relative reference frames. They were only thinking in terms of like I'm standing still, so like that's the reference frame. So it was very sort of counterintuitive to them at the time that it wasn't the absolute motion of the magnet or the wire that mattered. It was the relative motion between them. And especially in this third one, where just changing the magnetic field and not even changing the location of the wire or the magnet was producing the same effect. So this is basically what gave Einstein the idea to develop relativity. It was these experiments that really got him thinking about relative motion and what it means to have an absolute frame of reference. And in all three as well, we end up with the exact same equation that describes the current through the wire in each of these three situations, which seem totally different. So this is what gave Einstein really the idea for and got him thinking about relativity, was the fact that these three experiments all led to the exact same equation and basically the exact same physical outcome of current in the wire. So now let's look a little bit more closely at Ampere's law, and we're going to have to go back to capacitors for a minute. So Ampere's law doesn't hold for non-steady currents. So if we have a current that depends on time, so it's not steady in time, Ampere's law doesn't work. And that sort of makes sense because we really derived it from the Biot-Savart law, where we treated the current as constant, right? We could just pull this current out as a constant. It wasn't changing with time or anything. So let's think back to capacitors for a second, because our Ampere's law, as we have it, doesn't really tell the whole story. So if I have a capacitor like this, and I have some current going through my wires, and then I'm going to have some charge build up on the plates here. So we looked at this when we were doing capacitors in series and parallel. The current would bring some charge, deposit it on the plate, and then, keep going down the wire. But what's happening in here? So we don't really have anything to describe what's going on in here. Now, obviously, somehow something's happening between these plates because current flows through the whole circuit, even though there's not a wire through the whole circuit, right? It stops at the plate of each capacitor. So let's write down our electric field for a capacitor was sigma over epsilon naught. Now, I could rewrite this as the total charge divided by the area of each plate. And now I want to know how this electric field and the charge on these plates are changing with time. So now this is not the same really as when we were charging and discharging a capacitor through a resistor. We're just saying if we turn on the current in whatever circuit this is in, there'll be no charge on these plates at first. And then as more and more charge accumulates from this current I, we'll start getting an electric field between these plates, right? So we know that for a capacitor, when we have the charge build up on the plates, we're going to get an electric field that looks like that. So basically, how is that changing in time as our current and our charge builds up on these plates? So let's take the time derivative of the electric field here. Now, epsilon naught is not going to change with time, and our area of the plates is not going to change with time, but the charge on the plates will, right? Because as more time passes, once we turn that current on, more and more charge will build up here. So the time derivative will fall on the charge. And then we have a 1 over area over here. So what's the time derivative of charge? Well, we know the time derivative of charge. We already said that that was the current, right? So dq dt, we already said, was a current. So I can rewrite the change in the electric field now in terms of a current. And this sort of looks like a current density, right? So I'm going to just call this, so this looks like a current density because I over the area was equal to J. So now here I have something interesting. I have that a changing electric field looks like a current. And we know that a current will produce a magnetic field. So this is actually how a changing electric field can produce a magnetic field. Now let's look at another way to derive the same equation, but using flux. So again, I'm going to just write down my equation for a capacitor. The charge is just equal to the capacitance times the voltage. Now the capacitance, remember, I can rewrite as epsilon naught times the area of my plates divided by the distance between the plates. And the voltage I can rewrite as the electric field times the distance between my two plates. So I'm just going to substitute these two equations in here. So I have EA over D, and then I have E times D. See that my D's cancel. So I'm left with Q is equal to epsilon naught EA. Now again, I want to take the time derivative of this because I'm interested in how the charge is changing on the plates as charge builds up. So I'm going to take the time derivative of both sides. So I'm going to have dq dt on one side. And then my other side, epsilon naught doesn't get the derivative since it's just a constant. And so now I have d dt of the electric field times the area. And the electric field times the area, I know, is flux, right? So now I know that this dq dt is a current. So I'm going to call this little I with sub d. So this is actually going to be called the displacement current. And I can write it as epsilon naught times the change in the time rate of change in flux of the electric field. Okay, so this I'm calling my displacement current. Now this is exactly what I just found doing it this way here in the previous slide, where I could just rewrite d E dt is equal to 1 over epsilon naught. J is simply the current divided by the area. So you can see that I can just rewrite this and call this I, I'm going to call my displacement current instead of capital I. So these two equations I just found, or these two ways of deriving my displacement current, give me the same final formula. So this is my displacement current, so let's write that here. So this is our displacement current, little I sub d, and it's given by epsilon naught, and then the time derivative, I should have put, I put partial derivatives there, but I'll change that in the notes. So these should just be regular derivatives of the electric flux through some area. So this is caused by a changing electric field. So a changing electric field can induce a magnetic field. Now, again, it's a little bit confusing because it's called a displacement current, and it's not really a current, it's just a changing electric field. So Maxwell actually figured out there was various mathematical reasons that he wanted to amend Ampere's law and include this displacement current. Your book says that he pulled it out of thin air, but he really didn't. He had, mathematical justifications for wanting this to be included in Ampere's law. So we're left with the name displacement current, even though it's not really a current. And your book also calls the displacement current a fictitious current. So I just want to clarify that a little bit. The effects of it, the physical effects of it, are not fictitious. So when you have a changing electric field, it really does produce a magnetic field as if it were a current. Now, it's fictitious in the sense that it's not really a current because, when we have just an electric field changing between the plates of a capacitor, obviously there are no charges like flinging themselves from one plate to the other. So it's not a current in the sense that like there's charges flowing. But it does create a real magnetic field that you can test and predict the value of your magnetic field according to this equation. So the current part is fictitious, the physical effects are not. All right, so now we can rewrite Ampere's law in terms of these two contributions now. So we can rewrite Ampere's law still as the magnetic field integrated around a closed path is equal to mu naught. Now we have this little IC is just our regular current where it's just charges flowing, current through a wire. So this is the regular current, and then this is our displacement current, which is given by the change in flux of the electric field. So to find a total magnetic field in some region, you have to take both of these into account. So this is like the full form of Ampere's law. And again, this was Maxwell's big contribution to Maxwell's equations because other people had sort of figured out, Gauss's law was developed by Gauss. So other people had kind of, hobbled together some of the other equations. Maxwell sort of took them all, put them together, included this displacement current. And this was really sort of, including this displacement current was really pivotal in sort of unifying electricity and magnetism fully, and we'll see that more in a second. So now let's do an example using our full Ampere's law. So we're looking at a parallel plate capacitor. So we have two circular plates, each with some radius. We have a regular current going through the wires. So the current comes here, it deposits charge on the plate. That creates an electric field between the plates like we have with any capacitor. And then that changing electric field, so as charge builds up on these plates, that increases the electric field between them, and this changing electric field now creates a circular magnetic field that's curling around this changing electric field, just as you would expect if there was really a current here, right? Because when we have just a current carrying wire, we know that the magnetic field curls around that wire. So we have the exact same thing here where our magnetic field curls around the changing electric field. So let's figure out what the value of the magnetic field here is. So let's look at an Amperian loop. I want to find the magnetic field right here. So right in between here at this little radius r, what is the magnetic field there? So I can write down Ampere's law. Now, there's no actual current enclosed in my loop here, right? It's just an empty space between these two capacitors. So this current is 0, right? This current is up here in the wire, not over here. So I only have this displacement current to worry about. So my Ampere's law is going to be equal to just the enclosed displacement current. And my displacement current, I said, was epsilon naught times the change in flux. Let me write the flux first, of the electric field through some area. So we're looking at the electric flux through this circular area that is bounded by our Amperian loop. So, okay, so now how is my flux changing? So my flux, we know, is going to be equal to E times the area. So I know, first of all, that the time derivative here will just fall on the electric field, right? Because the area I'm looking at is not changing. So let's just write our constants out here. Then we're going to have dE dt times the area of our Amperian loop. So I'm going to be careful because this is the area enclosed by my loop. So we're looking at the flux that is through the area enclosed by our Amperian loop. So it's just this area here, not the area of the whole plates. So you have to be careful with that. So I'm going to write area loop. So this is our flux. But now how is my electric field changing? So let's first just write the electric field between these two plates. So that will just be the total charge on the plates divided by epsilon naught divided by the area. Now, this area is the area of the full plates, right? So this is the area of the full plate because here we have the surface charge density, so we need to take into account the full charge on the plates divided by the full area of the plates. So we have two different areas here, one from the flux going through the area of our Amperian loop, and then the area of the plates to find the electric field between these two plates. So when we take the time derivative of the electric field, that's only going to fall on this Q here. So dE dt is just going to be this. So only the Q will get the d dt, and this dQ dt is the current in our wires, since the charge on the plates is changing at the same rate that the current is depositing charge on it. So this we can rewrite as I sub C. This is our current coming in here. So now let's write things out a little bit more clearly. So we have mu naught epsilon naught. dE dt, we said here, was I sub C divided by epsilon naught divided by the area of the plate. And now we have our area of enclosed by the loop from the flux. So we can see right away that our epsilon naughts cancel, so let's cancel those out. So we've still got a mu naught, we still have an I sub C, but now our area of the loop is going to be pi r little r squared, right? Because we said that our Amperian loop was at some distance r here, so that's going to be little r, and then divided by the area of the entire plate, that's going to have capital R. So we have two different r's here we have to be careful about. And now we can do the left-hand side of our Ampere's law, which was just b times 2 pi little r, since it was just the loop here. And so now we have mu naught I sub C pi little r squared pi capital R squared, and then we can just solve this and get our magnetic field in between these two plates. So we can just solve for B, and we get mu naught I sub C our pi's cancel. So we get 1r up here. And then we have r squared over 2 pi r capital R. And so we can see that this simplifies to 2 pi r squared. Okay, so this is our magnetic field in between these two capacitor plates. As charge builds up on our plates, the electric field increases, and that forms a magnetic field of this magnitude curling around that change in electric field here. And this has been experimentally verified. So the displacement current, even though it's not proper to call it a current, it very much, the physical effects of it are very real. Okay, now let's do an example with this. All right, so for this example, we have a parallel air-filled capacitor, just like what we just looked at, is being charged. The circular plates have an area, a radius of 4 centimeters. And at some instant in time, the current in the wire is, so that means I sub C, is 0.520 amps. What is the displacement current density, JD, in the air space between the plates? So what is the displacement current density in between here? So the displacement current density. Now in our previous example, so if we look at this step here, we can see that this term here is a current density. So we have mu naught, and then we have IC over pi r squared, and then we had pi little r squared. So what this means is that this we can consider our displacement current density. The displacement current density fills up the entire area between the plates. So that will just look like a current divided by the area, the cross-sectional area of the plates. Now you can also go back and derive this the long way from the changing electric field, but this is sort of a shortcut because we can see here Ampere's law tells us that the magnetic field is just mu naught times the enclosed displacement current, and that's exactly what this looks like, right? It's just going to be mu naught times the enclosed, this is our Amperian loop here, the enclosed displacement current here, and we have a current divided by an area, which is a current density. So this is our current density in this case. So JD we can just write as the current in the wire divided by the area of the plates. And I'll put another way, if you want to derive it the long way, I'll put that in my full notes as well. So, okay, this is our current density. So if we want to plug this in, we need to plug some numbers in. So we have our current is 0.520 pi, and then r squared, I should make this capital R, is 0.04 squared. So this comes out to 103 amps per meter squared. So that's our displacement current density. Now, what is the rate at which the electric field between the plates is changing? So we saw also in our, when we were deriving the displacement current, we said that the change in the electric field with respect to time was equal to 1 over epsilon naught times our current density. So this is our change in electric field. So we can just rewrite that. So we had our dE dt was just equal to 1 over epsilon naught times our displacement current density, which means all we have to do is just divide our 103 amps per meter squared divided by epsilon naught. And we get for that that comes out to 1.6 times 10 to the 13 volts per meter per second for a changing electric field. Okay, so that is our change in electric field there. Now, we need what is the induced magnetic field between the plates at a distance of 2 centimeters from the axis? So since these plates are 4 centimeters, 2 centimeters, would be about here where R was drawn. So 2 centimeters is somewhere in there. So we can use the exact same equation that we just derived over here for the magnetic field that's formed between these plates. So our magnetic field, so we want to know B when R is 2 centimeters. So B, we said, was given by mu naught, the current in the wires, times the radius we're looking at, divided by 2 pi times the total radius of the plate squared. Okay, so we just have to plug in some numbers here. So mu naught is 4 pi times 10 to the 7. And then our current was 5.2 amps. The radius we're looking at is 0.02. Then we have 2 pi, and the full radius of our plates was 0.04 meters squared. So this comes out to 1.3 times 10 to the negative 6 Tesla. So that is our magnetic field at a point 2 centimeters from this central axis. And now we want to know, okay, what's the magnetic field 1 centimeter from this axis? So we do the exact same thing, but just plug in 1 centimeter here. So we'd have the exact same equation. We'd have 4 pi times 10 to the 7, 0.520, 0.01. So we have the same equation. Or you could just divide this answer by 2, since you're just changing this distance here. So either way, obviously, you'd get the same answer. So this comes out to 0.65 times 10 to the negative 6 Tesla. Okay, so that's a problem with the displacement current. So now let's just go back over, now that we've seen all of Maxwell's equations in all of their full form, let's just go back over these. So here we have the integral form of Maxwell's equations, and then this is the differential form if you've taken vector calculus. I think these are much easier to sort of get a visual picture for what's going on. So basically all of these equations, before Maxwell added the displacement current, so before we had that, our equations looked just like this. So these were sort of already known in one form or another before Maxwell put them all together, basically. And the reason why what he did, essentially just adding in the displacement current, was so important was if you look at, so I'm just going to use these equations since these are a little bit clearer. So if you just look at the 4 equations without the displacement current, you can see that, okay, a electric field is caused by a charge, and an electric field is also caused by a changing magnetic field. But according to these equations, a magnetic field can only be created by a current. So if you have a changing electric field, nothing will happen. So when Maxwell added in this displacement current, it added a symmetry to Maxwell's equations that wasn't previously there. Because now you can see that a changing magnetic field will cause an electric field, and a changing electric field will cause a magnetic field. And this fact is what allows basically electromagnetic waves to propagate. Because in space, you have just a constantly changing electric field, and that change in the electric field induces a magnetic field, which is changing. And that change in the magnetic field induces the electric field to change. And so these electromagnetic waves can just propagate forever, just sort of influencing each other and, just waving along. So if Maxwell didn't include, or he didn't sort of have the insight to add this displacement current term, we wouldn't be able to write electromagnetic waves as waves. So you can directly derive, like I said, you can derive the speed of light, and you can derive the wave equation from these four equations, but you need this displacement current term here. And then from this, you can derive that electricity and magnetism are the same force. They're both waves. They both travel at the speed of light, but this term is really vital. And if you take these so just with these four equations and the Lorentz force law, this describes every electromagnetic interaction that you can come across, whether it's an electromagnetic wave, whether it's two charged particles, whether it's a current, anything. Electromagnetism can be derived by just Maxwell's equations and the Lorentz force law. Okay, so that is it for all of our new material. Like I said, we'll do a review tomorrow and possibly another review, or at least office hours for sure, on Monday. But okay, so that is it, and I will see you guys tomorrow.